All right, ladies and gentlemen, check this out. We're going to look at an example of using Coulomb's law and apply this and see what's going to happen to a charge in a particular situation. So we have three charged particles, charge 1, charge 2, and charge 3, arranged like this. Each charge is given, each particle has a given charge of positive 1.8 microcoulombs. And one more bit of information we're going to need to know is how far apart the charges are placed. So the distance between charge 1 and 2 is going to be 0.25 meters. The distance between charge 1 and 3 will also be 0.25 meters. And we're asked, what is the net electric force acting on charge number 1, acting on this guy right here? So we want to realize, first of all the charges have the same amount of charge, all the same type of charge. And so all being positive, what we can definitely say is, well, charge 1 and 2 will be repelling each other. So the force between these guys will work this way. And this is the force of charge right here. We're concerned with charge number 1. So this is the force of charge 2 on charge 1. 2 on 1. Also, we know, comparing charge 1 and charge 3, they also are like charges. They will repel. And again, we're only concerned with charge number 1 in this problem. So this force acting on charge number 1 is the force of 3 acting on 1. And so our job is to figure out the net force acting on charge number 1. So the net force sure looks like it's going to be something like this, right? There's net force, roughly speaking. So I have a couple things to keep in mind. I'm dealing with forces acting on an object. Remember, it's really just this object I'm concerned with. Just charge number 1 that I'm concerned with. But with forces acting on an object, and I'm clearly, specifically want the net force. I'm going to have a strategy in mind. So strategy to solve this problem, I'm clearly going to want to do a free body diagram. Also, I am going to probably need to use some geometry, maybe some simple trick, right? So I will probably end up solving for force of 3 on 1 and for force of 2 on 1. And I will likely use those as the components of the net force, right? So I'll solve for those two forces and then use them to find, net force, because they will be components of F net. That's what I'm going to do. Here we go. Free body diagram time. Couple simple axes. There's charge number 1, and I know that I have a force this direction from charge 3 acting on charge 1. I also know I have a force this direction from charge 2 acting on 1. And since I've got color, I can use it. I'm going to go green all over again, and the net force will be somewhere down here, right? Net force. Awesome. So now I'm going to look at the situation and solve for each of these individual forces here. Force of 2 on 1. It's the constant times charge of one of them, so charge number 1 and charge number 2 divided by the distance between them squared. I'm only going to write that equation once so I can remember it and not screw it up, right? So that's 9.0 times 10 to the 9. That is Newton meter squared per Coulomb squared right there, right? And now the charge. I have a charge of positive 1.8 microcoulombs in each of these particles. So 1.8 microcoulombs, that's going to be times 10 to the negative 6 coulombs. The other charge is the same value, 1.8 times 10 to the negative 6 coulombs. And the distance between them, 0.25 meters. And that is squared. Handy dandy calculator, and it tells me that this force of 2 on 1 is equal to 0.467 newtons. Just under half a newton. Okay, somewhat substantial. I also want to figure out the force of 3 on 1. So a little bit of clearing some space. Oh, by the way, on a test, if you have to kind of do one thing and then you've got some awkward space, not sequential, not one after the other, but sort of weird like this, a little faint line like this to separate what you're doing in one area from what you're doing in another area, very helpful to the person grading your test. Makes it easier to follow what you're doing. So this force, okay, I have to recognize that I've got the same charge over here. Charge 3 is actually the same as charge 2. And charge 1 is still charge 1. So it will be the same two numbers here. They are the same distance apart, the 0.25 meters, as it was here. So that's the same, and that is a constant, so that's the same. So look at this, I can save myself some math and just do that. Okay, so if I don't recognize that, then maybe I can write a statement about since all charges are equal and equally spaced, all forces acting on charge 1 are the same. Or maybe I should just say are equal. That sounds a little better. Notice it didn't just say all forces, because there would be a force between charge 2 and 3. Oh, yes, there would be. And they would repel each other, some fashion like that, but that force would not be equal to the other force, to the forces acting on charge 1. It'd be different. There's a different distance between those two guys. So anyway, back to the problem. A statement like this allows me to just go there. Boom. Now, the next step, I have the two components of the force. I need to find that net force. So that's not so bad. I can represent this with a quick triangle. Since I know those are equal, I draw two equal sides of a right triangle. And so there's my net force that I want. And how do I find that? That's just Pythagorean theorem. Show the work, show the work, show the work. Okay, so force of 2 of 1 squared and force of 3 of 1 squared. Brilliant. Gonna get an answer of 0.660 newtons. Boom. Is good. Right there. I have an answer. I put it in the box because I want my teacher to see it. Now, I'm only partially done. That's only half of the answer. This is a force, it's a vector, it has a direction. And I need to indicate that direction. I'll just do this. I'll put a theta symbol there for an angle. What is the value of theta? So that's pretty easy. If I have side and side, and I want to find theta right there, well, that's just, tangent of theta is equal to that side divided by that side, opposite over adjacent. Sure. So that means theta is equal to inverse tangent of this opposite side, which was force of 2 on 1, divided by that side, which is force of 3 on 1. Now, this makes it pretty straightforward because I know those two forces are equal. I got the same answer in each case, so that's just 1 over 1. That means inverse tangent of 1. And that's, if I don't have that memorized, the calculator's real quick going to tell me that's a 45-degree angle. So 45 degrees below the negative x-axis, right? I really ought to be specific. So I have the value of the force, 0.660 newtons, and I have the direction of that force, 45 degrees below the negative x-axis. Done. Boom. And so I have found the value of the net force acting on charge number 1. I could go on. Didn't have to, but I could. I could find that force acting on this guy in the same manner. It's just some basic skills, right? Net force from components, Pythagorean theorem, some easy basic trick, right? But the primary use of a formula that is a physics-related formula was this guy right here, Coulomb's law. Yes. So you can see Coulomb's law, Pythagorean theorem, some trig, and all coming together for us. That's it for now. Thanks for watching. Catch you next time.